I will try to condense this just a little bit. I do teach a semester-long course on demand analyses, and trying to fit an entire semester into an hour is difficult enough as it is. So I'll just start by saying that there's a lot I'm going to cover, and I'm going to share resources with you so you can really dig a little bit deeper into each of these areas. So I'm not going to get into the nuances of that hows or whys of some of these analyses. So, I will share those papers with you so that you can look those up on your own. So consider this just a brief overview of all of the different nuances that you need to consider and kind of the best strategies for doing demand analyses. I'll also add that really I should have some co-authors on this presentation, Brent Kaplan and Sean Gilroy, and I have a Slack channel where we talk about demand analyses pretty frequently every day. So they've really greatly shaped my thinking in all of this. And then obviously there's a host of other individuals that I talk to quite frequently about this stuff. So their names are also appearing on the screen. Co-authors on many papers, but also kind of my go-to sounding boards for when I'm stuck in my own analyses. So the presentation for today is going to really focus on 3 areas. First, I'm going to cover just a primer on demand analyses in general and what the equation means. I will then introduce some modulators of behavioral economic demand, mostly like from the basic experimental literature, and then provide some recommendations and resources for demand analyses. Some best practices. Some of these will be my own opinion, and I will make sure to alert you when that is the case. So let me start by just giving a brief primer on demand analysis and what demand means. I'm going to share a table with you and just kind of go through some basic definitions. And this comes from Brent Kaplan's paper for his B's demand R package for doing demand analyses. And so you might want to check this out. This is one of my highly recommended readings I'll be sharing at the end. This table will kind of define some terms as we move forward. Most of these you've heard already today, but I want to dig a little bit deeper into some of these. So what I'm going to do is just go through each of these line by line, not really get into too much detail, but talk to you about what the symbol is for the term, whether it's an observed or derived parameter, and kind of what we're doing when we look at these. So first is intensity, and we've heard that discussed frequently and across all of the talks today. And so Q naught or Q sub 0 or Q 0, you'll hear people refer to it that way. This can be observed or derived, meaning we can take an observed value of this by what the participant actually tells us their intensity of demand is, which is the level of consumption or their likelihood of purchasing at low or no cost. So this is our maximum demand, the intercept of the demand curve. This is where the demand curve starts, and then it all goes down from there. We can also derive that by solving for what that intercept should be. And there's some considerations you might want to make with that. I don't have any slides for this, but if you're doing probability of purchase, you should set a cap of 100 or 1.0, depending on how you're doing things as a proportion or a percentage. You shouldn't have greater than 100% likelihood of purchasing something. So you have to use some kind of logic there and some common sense when you're doing those sort of caps. Next is K. I have a lot of stuff to say about the K parameter. So I'm just going to quickly talk about that. This is our range of consumption. So this is kind of the span of the demand curve. Again, it can be observed or derived, meaning we can constrain K to be a particular value that we can assess and calculate, or we can derive it and let the model and the nonlinear regression actually tell us what K should be. So we'll hold some more discussion for that for later. Alpha is the big one. And this is something that, when people are doing demand analyses and fitting curves to data, it's because we want to get this measure of alpha. And alpha is a derived parameter. There's really no observed way to get this. And this is the rate of change in elasticity across the demand curve. So it's inversely related to value. So if you have a very small alpha, that means that demand curve is persisting pretty strongly. So you have a lot of inelastic demand. So that demand curve is flat for quite a while before it eventually starts to drop. And it does drop slowly if there is a low alpha. Generalized essential value, I'm just going to kind of skip over this for now. I'm not going to spend too much more time talking about it, but this is very much just related to alpha. Breakpoint is something you've heard about today. There are actually a couple different ways we can get breakpoint. Breakpoint 1 is the highest price in which there's any consumption or likelihood of purchase, whereas breakpoint 0 is the first price at which there is no consumption. And this is important for discussing and being sure that when you're sharing your results, you're clear about what kind of breakpoint you're reporting. So often if we get to a point in a demand curve where we haven't assessed enough prices, demand has not reached 0, then breakpoint 1 is often what will be used because that is basically the last price in the price sequence. So something to keep in mind. Again, read the B's demand paper for a little bit more information on that. The Roma, Hirsch, and Hudja paper that Michael had talked about earlier today first introduced kind of the distinction between these two terms. So you might want to write that down and check that out later too if breakpoint is something that you're working with. And then we have Pmax and Omax, and I'm going to get a little bit deeper into that when I walk through the demand curve itself. But Pmax is going to be essentially your maximum price. So that's the price that's associated with unit elasticity or the point at which we move from inelastic to elastic demand. And I have some slides on this. And then Omax is the price that is associated with that. And there is some more nuance to that as well that I'll discuss later. All right, so one of the first things I'm going to do is really talk about this idea of elasticity and alpha. And this is a paper that was recently published by Sean Gilroy et al. And these, if you really want to get deep into how behavioral economic demand relates to traditional economic demand, this paper kind of walks through that. But there's a very important piece to this paper and something that I'm hoping we can all agree on today moving forward in terms of our language. So ADA is on the screen, and that is a term that represents elasticity. And so as we start to talk about alpha and we start to talk about what a demand curve gives you, it's important to recognize that elasticity is ADA. And ADA is going to be solved by essentially taking the slope between all the different points. So at any given price or change in price, we get a change in consumption. So elasticity is simply the change in consumption over the change in price. That is ADA. So there is basically an infinite number of ADAs and elasticity values across a fitted demand curve. So I mention this because we often talk about elasticity being interchangeable with alpha, and that is just simply not accurate. I'm guilty of it myself in my own papers, but we're trying to clean that up a little bit. Alpha is not the same as elasticity. What alpha is basically how elasticity changes. So you could think of it as the change in ADA over a demand curve. So this is one of the major points of my talk today is to try to get everyone to at least talk about it this way. I've worked with economists and they get confused when they read our papers. So I just want to make sure that we're on the same page here. So my little take home point is please stop referring to alpha as elasticity. It's not quite accurate. What ADA can tell us though is different kinds of elasticity. And when we're talking about inelastic demand, ADA is less than 1.0. And I have a figure for this in a moment. Elastic demand is when ADA is greater than 1.0. And I mentioned to you before, Pmax, that's the point at which you get that shift. So if you look across a demand curve, it's chugging along and decreasing exponentially. ADA is changing throughout that, which is our alpha term. And so the point at which there is an exact one-to-one correspondence between a change in consumption in log units and a change in price in log units, that point elasticity is 1.00. So ADA is equal to 1.00. And that conceptually is what Pmax represents. So that is the price that gets you a 1 unit increase in price and a 1 unit decrease in consumption in log units. And so that's important to keep in mind. So everything to the left of that is inelastic demand. Everything to the right of that is where demand becomes elastic and you're getting more change in consumption with just 1 unit increase in price. All right, so the model itself, there's plenty of competing models out there now, and I'll share a few of those towards the end of this presentation. But where this all essentially started is in the Hirsch and Silberberg paper about economic demand and the exponential approach. So I'm going to walk through this in really basic terms. I've been going fast so far to make up some time, but I'm going to slow down right now. So when we're talking about this equation, we need to understand what's going on. And so, a lot of people who do behavioral work shy away from doing quantitative modeling because you don't want to lose sort of that relation to behavior. You don't want to get it lost in symbols and in mathematical models. But I will show you that this model incorporates all of that. So this log Q that is on the left side of the equation represents our behavior prediction. So our goal when fitting a curve is to predict behavior. We're predicting behavior within the boundaries of what we're assessing. In this case, it would be price or other aspects of unit price when we're looking at a commodity or a drug. So our goal is to predict a level of consumption. So Q is going to represent consumption, then the quantity consumed. So that's where the Q comes from, is quantity. And then to the right of that are basically the things that we can measure or that we can manipulate in our experiments. So these are environmental influences and independent variables. So again, behavior analysts who are interested in behavioral economics, these are the things that we are controlling in the environment to produce behavior change. And so all of those then get filtered into that right side of the equation. And I'm going to walk through this in even greater detail now. So when I say that there's a behavior prediction, I'm talking about Q. And Q is simply consumption of reinforcers. So that is the target behavior of any demand analysis, is Q. So moving along, we have some predictor variables that we have to plug into this equation. And so what you'll see on the right are things that we use to kind of create a constant or to help standardize the curve a little bit for our participant. So that Q naught, Q sub 0, Q 0, however you want to define it, that is consumption at minimal cost or free. I mentioned before, you can leave this as a fitted parameter, or if you're actually asking participants to textually or verbally state how much they would consume if something was free, you can actually use their actual self-report value here. So this sets the origin of the demand curve, your y-intercept. And there's an important piece to the exponent in this equation. And this is where we're standardizing for someone's intensity of the demand and its interaction with price. And so if we have that as that exponent, so Q naught times price as a term in that exponent, it helps us compare between participants with different intensity values. So we can then look at things like alpha between participants who have differing intensities. So that Q naught and Q naught by price term allows us to do this. Intensity, I also like to think of that as like the defense of someone's bliss point. So if you had free access to a commodity and you could consume it at no cost, what would be your bliss point for that? And the idea is, as soon as you start to insert disruptors or pressures to prevent consumption, that's where demand starts to be assessed. And that is the degree to which we continue to consume that in the face of those costs or those effort requirements. Okay, so moving along here, there are some terms in here, and this is where often people who are not quantitatively well-versed might steer away from doing these kinds of analyses. And in particular, we have some of these things that we might not know what they mean, or they're reminiscent of our times in calculus or differential equation courses we might have had back in college. But we have some logarithmic transformations that happen. And we also have that E, which is Euler's constant, and this -1 that's in there. Now, these are all in there to basically organize that period of inelasticity into a straight line. Won't get in the nuances of that. Again, the papers I'm sharing with you or recommending you read, we'll get into those details more greatly. So I do recommend that you think about that. I'll also say that that equal sign is important, and we often take this for granted when we look at equations, but the equal sign implies an invariant relationship. And I say that because sometimes we lose sight of what the kind of narrative story is that a quantitative model is trying to tell us. So what this is doing is saying that if we know that there is no price, so if we look at that P term over here, if we cancel out all of this stuff to the right of that plus sign, because there's no price, then consumption should equal intensity. They should be invariant. Those should be equal. And so this then tells us that. So that has to set that core functional relation. K is something that is very annoying to a lot of demand researchers. You've probably come across issues of this when you've tried to fit your own curves. We're going to talk about that in a little bit, but it is simply the range of the function. So it will specify from Q0 or Q0 down to where it meets its asymptote. And so that K value sets that span of the curve. And so K is critically important in fitting the data. The problem is there's not really any standards for how to best calculate K. And so things can get pretty hairy when you start to analyze your data and you don't necessarily know how to specify K, or if you're pooling data across participants who have different K values. And I'll talk about that in a bit. And then our important piece here is our modulating variable, which is alpha. And this describes the rate of change in elasticity across the entire demand function. There's a reason that we've kind of used this synonymously with alpha or with elasticity in the past, is because this kind of captures what we're talking about when we say that we're looking at demand elasticity. Alpha is just quantifying that. All right, so quickly gonna walk through where these things kind of show up in a demand curve. So when we talk about intensity of demand, or Q0, that is going to be theoretically the consumption at free. So when there's minimal cost. This is where the demand curve starts. And so this is a relative term for the most part. There's no correct answer for what is a high intensity or a low intensity. It's relative compared to your control group or a control condition. So this light blue line represents what we would consider high intensity. This dark blue line represents what we would consider relatively low intensity. So one is just greater than the other. So it's just a relative term. All right, so moving along our demand curve, let's talk about K. So the best sort of approach for just handling K in general is to take the log range of consumption. And so a way we can do that is just find our maximum consumption and our minimum consumption value and divide, and we take the log of that span. So if we have a maximum consumption of 100, and we look at our demand curves and our minimum consumption is 1, then we're simply looking at the maximum being 100, the minimum being 1. So we take 100 divided by 1, that's 100, and we take the log of that. And so this would tell us that K should equal 2. That's what K represents, is that log span. All right, so we put that in there so that we can appropriately span the curve. And now we need to take a look at what alpha tells us. So this is our change in elasticity. And so this is essentially looking at how quickly that demand curve drops. And so, like I had mentioned before, we have Q0 and that interaction with price and the exponent to kind of help standardize things. So even if people have different intensities, we can still compare their alpha values. And so we can see here that one alpha is greater than the other. As you can see the difference in those curves, despite the fact they started at different points. We can make that comparison given that the equation has those built-in features. Okay, so moving along, so we have a low alpha here, a high alpha here. Remember that this is inversely related to what you kind of conceptualize as demand. All right, and then some other really important features of this as we move forward is the concept of unit price. Again, something we often take for granted. Unit price is essentially the cost-benefit ratio of a reinforcer. So we might have a fixed ratio number. So on FR1, one lever press gets you one reinforcer. So that would be FR1 divided by one SR plus. So unit price of 1 is one response for one reinforcer. So we can look at that here and we could say when unit price is 1, our participant or subject consumes 80 of those reinforcers. So now we can increase the unit price to 2. The simplest way to do that is to simply increase the response requirement to 2. And so that tells you kind of what would happen there. So we look at a unit price of 2, and we see that just 1 unit increase in unit price, we get a change from 80 down to 52. Now, another way that you can get unit price, though, is that you can hold the response requirement constant and actually manipulate the reinforcer magnitude. So if you wanted to get a unit price of 2, you could have 1 response, but now give half the amount of the reinforcer. And so that conceptually is the same thing as 2 responses for 1 reinforcer. And so there's some basic studies on that. There's not a lot of human work or purchase task work that's really explored that yet. And there is good reason to believe, perhaps, that cognitive biases from the more, traditional world of behavioral economics and in popular psychology, those might differ in terms of how we frame the unit price. And there has been some work from Brent Kaplan who's looked at that with like happy hour specials with alcohol, that the way you frame the unit price could matter because we have this ability to verbally respond and to interpret things verbally, whereas maybe a rodent or a pigeon would not be able to do that. And so unit price might be theoretically more consistent in non-humans, but with humans, we have to factor in our own interpretation and perceptual biases. All right. Sorry for moving through this so quickly. I mentioned before that we can look at elasticity values across a demand curve. And at some point, you will get an elasticity value that's exactly -1 in this log-log space. So 1 unit price increase is met with a 1 log unit decrease in consumption. That is exactly a 1-to-1 correspondence. So that's a slope of -1. Now, conceptually, what that means is everything to the left of that unit price is part of the inelastic portion of the demand curve, where a 1 unit increase in price is met with less than 1 unit decrease in consumption. When we get past that Pmax, or that maximum price, things become elastic. So now we're getting greater than 1 unit decrease in consumption with each 1 unit increase in price. So that is that maximum price I had mentioned earlier. And Pmax, or maximum price, actually tells us something else that's really useful, especially if you're talking about generating revenue or other policy concerns that you might want to be modeling, is we can look at expected output or expenditure. So if we basically calculate consumption of reinforcers, so the Q at each price, by that unit price, we can figure out how much behavior is being outputted by the subject. And so this creates a work function, which you see in the red. And so the work function is expenditure. And what you'll see is that when the demand curve has Pmax, the work function at that same price has the maximum output, or Omax. So that occurs right there. So if your goal is to perhaps try to convince policymakers of some excise tax on a commodity, like cigarettes, for example, one thing that you can sell them on is the idea of expected tax revenue, and you could generate that from the work function of a demand curve analysis. Now, I will get into a little bit more of this later, but there have been some advances in this work in mixed effects modeling of behavioral economic demand, and this is like literally hot off the presses just a few weeks ago, appeared online. This is important stuff, and I'll briefly cover it later. I'm putting this here as basically a placeholder to remind you, like, that's the basic, what I've told you is the basic sort of approach to demand analysis, but we can get a little bit more precise and a little bit more robust if we take it into mixed effects modeling. All right, I'm going to quickly then go through this idea of cross-price elasticity as a major modulator of behavioral economic demand. So when we talk about closed economies, for instance, when we try to close the economy in a purchase task, kind of like what Michael had talked about earlier, Liz, in terms of trying to put constraints in what the participant's imagining when they read the vignette, we basically say there's no availability of substitutes. Everything you're purchasing in this scenario has to be purchased in this scenario only. You can't buy this product anywhere else. That is creating a closed economy. And there is a robust literature on this in the basic literature, not a whole lot in the purchase task literature yet. But what we can do is basically look at performance and demand under a closed economy. And then we can look at what happens when you create the availability of substitutes, where you open the economy up. And so theoretically, what happens is you get this shift in alpha. You don't necessarily see a major shift in intensity, but where you'll see the most amount of change is in that alpha value. And so just to kind of show you, this is some work with non-humans that Hirsch tends to use in many of his writings. And you see this is performance under a closed economy with the square data points, which is essentially they can only earn the food during the experimental session. And then there is an open economy where the organism can earn food for free 1 hour outside of the experimental session. So that's an open economy. And what you see is, just as I had alluded to, theoretically, you see this shift in alpha. And that is a highly sensitive parameter to the idea of an economy type. And so you see that shift in alpha, but not necessarily any shift in intensity of demand. All right. And I will also note that Pmax is pretty much directly related to alpha. And so anything that's going to really dramatically affect alpha is going to also dramatically affect Pmax. Okay. This is just a quick tip for you. This is a great paper that is really underappreciated. This is by Imam in 1993 in the Journal of the Experimental Analysis of Behavior. And he basically offers a theoretical account of ways we can quantify the openness of an economy type. And I just want to put this here so that you can look it up on your own. But it's pretty clever, and it, I think, is good fodder for us to do some kind of basic research on open and closed economies, where we can actually try to quantify how open that economy might be or how closed that economy might be. So anyways, I won't get into the details of that right now. But I will just go through some basic examples, kind of using the logic of the Imam paper to talk to you about how the demand curve shifts. And so we heard about this when talking about kind of illicit commodities or legalization and what that might do to the demand for commodities. So let's say we have two commodities, the red circle and the blue circle, and these are perfect substitutes for one another. So these are essentially the same item. What does that look like? So I'm going to just kind of show you some scenarios here and walk through it. And my running example here will use a target commodity of plain tortilla chips. This is often used in some of the writings. And so what we want to do is take that target commodity and increase the price of that. So we put in place a purchase task, and there's an ascending price sequence where plain tortilla chips get more expensive. But now let's introduce a perfect substitute that's available at a fixed price. So at each increase in price for the plain tortilla chips, in this case, we have other plain tortilla chips out of a different bag or something. And these are available for a fixed price. So each time the price increases, the price stays the same for the alternative. And so what we should see here is that when there are perfect substitutes, you should see a very clean cross-price elasticity sort of plot. So the red plot is our plain tortilla chips that are increasing in price. And what you see is that as soon as there's any substantial change in the price, the plain tortilla chips at the fixed price will start to increase in consumption. And usually what you'll see is people have a budget of how much they're willing to spend on something. And so they're basically just optimizing their budget in terms of how many plain tortilla chips they can purchase. One of the important pieces of this is that you might not necessarily see any consumption during the really inelastic portion of the demand curve for the target commodity. But as the prices increase, you'll see that it had an asymptote at the top. So basically it will reach intensity. So if intensity is as strong as we think it is and robust as we think it is, then the alternative should then be consumed at that point once the target commodity is no longer being consumed. Now, not everything is a perfect substitute, and rarely do we find perfect substitutes. So let's talk about imperfect substitutes or partial substitutes. So in this case, we might have plain tortilla chips, and then we have a different brand of tortilla chips, or we have lime tortilla chips, or something that's not quite the same. And what you'll see is an effect that's very similar, except it now does not reach that asymptote that we see at Q0. So we'll never get to that intensity value because it's not the same commodity. It's an imperfect substitute. And so you will see that change right there. Now we have two more sort of relationships that can happen. So this next one are going to be complements. These are no longer the same commodity per se. This is a different commodity that technically would have a different value to the consumer. So this might be guacamole if we're talking about tortilla chips. So a complement is something that basically shares the same sort of demand structure. So even though the guacamole is available at a fixed price, as demand decreases for plain tortilla chips, you might see demand for guacamole also decrease because those kind of go hand in hand. So we often can see that if we want to figure out how two commodities might interact or might be related, doing these cross-price elasticity analyses and simply looking at the demand curve can inform you on whether or not it's a substitute or a complement. In this case, we say complementary relation because it follows the same sort of negative slope. And then finally, we have independent commodities. So these are things that have no relation to one another in terms of consumption and valuation. Now, in this case, I'll pick something silly like shoelaces and tortilla chips, which should have no bearing on one another. But often we assume that certain drugs might be related or might be shared, and they might not be. And these might actually be independent to your subjects. And so unless you do a cross-price elasticity analysis to look at this, you don't know that, and you're just making assumptions. So in this sort of case, demand for the shoelaces stays fixed. And it doesn't matter what happens with your demand for tortilla chips, it's never going to change your demand for shoelaces. And so this would inform us that these are independent of one another. And so this cross-price elasticity work in addiction can be very helpful for policy purposes, where we might be able to regulate a certain commodity and get collateral effects in the policy on other commodities that we want to try to mitigate. And so this work remains to be explored for the most part. So I'm hoping someone here will take that up. All right, so what I think is the most important part of my presentation are these recommendations and resources. So I'm going to kind of slow things down a little bit here and walk through these. So I think the bulk of emails that I receive about demand curve analyses are going to be related to these issues. Okay, so first up is this issue of zeros in demand work. And this is what happens when we have a consumption value of 0, Q equals 0. And we'll walk through why that's an issue now. So theoretically, we need to think, what is the operant response that we're looking at? So Hirsch and Silberberg, in the original formulation of the exponential model, were looking at aggregated response patterns from non-humans in which they're pressing levers and earning rewards. So in that case, a non-human non-response is not a response. So it's the lack of a response. From a strict Hertzsteinian, if you're into the matching law work, sort of perspective, they're engaging in other behaviors and responding to other stimuli, so that there is behavior there, but it's not being tracked in our analysis. So a non-human non-response doesn't exist in that sort of EAB world. We don't quantify that. So they didn't run into the theoretical issue of a 0 response. So what happened, though, as Michael alluded to earlier with that really nice timeline of how we've assessed demand, is that we moved to basically verbally asking human participants how much they would consume at free. So now we actually can get a response from a human that says 0. And so this becomes a theoretical issue of what is a human response of 0? Is that an actual response, or is it the lack of a response? I would err on the side of saying that any response from a participant should be treated as a response. This is verbal behavior. The participant is telling you their preference and their projected sort of consumption profile. So this then creates issues, because now we have this exponential model that wasn't made to handle zeros, and now we're trying to force it to handle zeros. And the reason that this is an issue is because we have that log scale that kind of makes that inelastic portion of the demand curve flat. And so log of 0 cannot exist. And so this has posed some problems in the analysis of operant demand. So there's a couple approaches that you can take. Some probably shouldn't do, some are better than others. So, a very strict approach that happened for a while is just to simply stop at the last non-zero consumption value. So even if you're looking at a purchase task and you've got a participant saying, I will not purchase any joints, I will not purchase any beers or whatever in your purchase task, you just then ignore all those zeros. So that would kind of be like the Hirsch equation handling of that sort of situation. Now, there are some new approaches that you have at your disposal, and I'll talk about these a little bit later on. Mickey Coffernis and colleagues have an exponentiated model of demand that theoretically handles zeros. And there's also a zero-bounded model of demand, what we call ZBE, that can also handle zeros. And so those are options that you have in terms of modeling. Another approach that people have taken is to simply add a constant so that there's never a zero. So you arbitrarily pick something like 0.01 or 0.001. It probably shouldn't be arbitrary, but that's what we tend to do. And that can actually really mess things up. But that's historically been a solution that people found convenient and easy. I've published those sort of constants, but I've learned my lesson, and some smarter people than me have told me that that was probably a really bad idea, and they've convinced me. So we want to hold this thought now about this issue of zeros, because this is related to one of the other big issues in demand analysis, and that is this issue of K. So as I mentioned before, K is that span parameter. It basically sets the boundaries of intensity and the asymptote of demand. And sometimes if you look at demand curves, you might see kind of an S-shaped demand curve where it's inelastic, it curves down, and then it fishtails off at the end. That's often because K is forcing it to do that, because that's the role of K, is to stop the demand curve. So this poses some issues. Conceptually, K is simply the range of consumption in log units. It can be observed or it can be derived. We can solve for K, or we can tell the equation what K should be. There's really no standard approach to that. And so researchers are kind of left figuring out what to do. And unfortunately, what we often do is we mess around with K until the demand curve actually fits. But at that point, you can kind of be engaging in p-hacking a little bit because you're fishing for a good approach to K. So that's a problem. I just want to do a visual for you of some of these issues with K and adding that constant. One of the resources I'll share at the very end is my lab website, where I have this visualization tool where you can basically pull up a spreadsheet and then try different parameters and see what that does to the shape of a demand curve. And so I just simulated that here into a screen recording. So here we have something with intensity of 100, K of 2, and a set alpha. And you see what the demand curve looks like with a K of 2. So let's assume that we're going to hold intensity constant and alpha constant. And let's just change the span. What you've now done is stretched the demand curve. Now, technically, that should affect alpha, but the way Pmax and Omax are calculated, it does incorporate K. So that's actually changing our Pmax and Omax based on K, even though alpha is technically the same. So again, depending on how you're calculating these things, you're going to get a very distorted view of demand. And so, you might be thinking, well, why would K change like that? So this would be an example of a K of 2, but now you're going to say, like, well, let's arbitrarily add a 0.01 to everything so that we don't have any zeros. You're now imposing a different floor to that K span, and you're stretching that curve. And so what you're going to do is distort demand at that point. So that's not ideal. So we've got to deal with that. So what do you do with K? Well, you could do the log span. So Hirsch et al. And Coffernus et al. Kind of handle that the same way. So log of max over min. Another approach, though, is to treat it as a free parameter. So you can simply tell the curve or tell the equation and the modeling software to solve for K. An issue with that is now you're adding an additional free parameter to your modeling, which isn't ideal. So that might not be a great solution either. There's also this approach that we've advocated for. I think it's in the B's demand paper, where you take the log span and add a constant of 0.5 with the assumption that maybe we didn't assess a high enough price sequence. And so we want to add just a little bit of wiggle room for K. So you could add 0.5 to whatever your K is. So again, that kind of seems a little arbitrary, so that might not be ideal either. And so, we have to think about what that can do. So what I would advocate is if you really want to dig into this issue and to fully understand the demand model, you should check out the B's demand paper by Brent Kaplan et al. There is almost an entire page devoted to the issue of K. So this is a very serious consideration when you're doing demand modeling. It's not just as an easy sort of arbitrary thing that you hold as a constant. And in the Coffernus et al. Paper that proposed the exponentiated model of demand, he actually did simulations to show you how adding an arbitrary non-zero value to your zeros actually distorts demand. And I won't get into that. This visual will kind of show that for you. So that's not ideal either. So then you're left, well, what do we do? The great thing, and I'm not just plugging this because I was a co-author on it, but the great thing about the new model, the zero bounded model, is that you don't really even need K in one of the approaches. So I'll talk a little bit more about that later. Big piece I want to leave you with is do not just pick 4.0. Early on, a lot of people did that because the original Hirsch template in GraphPad Prism used that as the K value. And so you'll still see that pop up in some papers where K is exactly 4.0. Maybe it actually was, but that's a pretty large span if you think about log changes. So anyways, that being said, I want to also just share some thoughts on this. We don't really know yet, there hasn't been direct research on this, of these different approaches to K or handling of zeros on latent factors. So the zero bounded model, I don't know. We don't know how the latent factors of persistence and amplitude that Gideon talked about, how those will emerge if we're avoiding K, because it's so the other papers that have done that have relied on K in their modeling. So we don't know. That needs to be done. So that leads me to discussion of alternative models, because this is important. And these alternative models have been developed in recent years to try to get around some of these issues. So again, the original Hirsch and Silberberg is kind of the starting point. The next iteration was by Mickey Coffernus and colleagues. And this was just simply taking 10 to the power of everything to get rid of the logs. And that kind of solves the issue of the zeros. And what Mickey showed in some of the simulations that he published is that the EXP, the exponentiated model that you see at the bottom there, actually resolved the true demand elasticity values better than all of the Hirsch and Silberberg approaches that you can do. Now, if you read the zero bounded model of operant demand, it kind of gets into some of the issues with potentially doing that. And one of those is that it's debated as to whether or not you can actually hit zero in that curve. Well, you can't theoretically. And so what Sean Gilroy had come up with is an inverse hyperbolic sine sort of approach. And you can see it on the screen here. I'm not going to get into the details of it, but it's a very simple iteration of the exponential demand model where you do this simple inverse hyperbolic sine transformation. And there's templates you can download to do this. You can use his software to do this. It's fairly straightforward. And this will then allow you to theoretically actually model zero consumption. So that's one solution. And you no longer have K to contend with, and all of those decision rules have to go with that. And then just to show that I'm not making this up, here are some data sets that show that using the different replacement techniques, you actually still get the same alpha values with the ZBE model. So quick little notes here, Sean Gilroy, personal communication, some tips that he recommended to me as I was throwing these slides together, that you should actually do a model selection approach to compare whether or not you need a zero bounded, the inverse hyperbolic sign with a K versus without a K. So you can actually do that to see if the curve fit, dramatically changes. And then also to compare that to a null curve, so kind of like a noise comparison where there's no elasticity. And so do you actually need alpha? So this is an approach. If you read the ZBE paper, you'll get a little bit more into this. All right. Now, this is where I'm going to kind of gloss over some things. Luckily, we have the authors of some papers on here. So if I can't answer a question, hopefully they will. At this point, everything we've talked about is assuming you're analyzing an individual data set. We have our consumption values, we have prices, we fit a curve. The problem is most of us are interested in large groups of participants or repeated measurements or between conditions. And so now you're not analyzing just one data set, you're analyzing an aggregation. And that comes with some decision rules that you have to think about that have some dramatic changes in the quality and accuracy of your data. So this is where the mixed effects modeling approach becomes very important. And for a long time, I was doing this approach called fit to group or fit to mean, where you basically average all the consumption values across your participants and fit a curve to those averages as if it's a single participant. Now, the issue there is that you're not actually taking into consideration variability, and the model doesn't know that what you're doing is modeling a group or an aggregate pool of data. Rather, it just thinks it's one more participant. So this is why you're going to see those R squared values of 0.99 that we often think like, well, this is because we're really robust demand modelers here. That's just a function of you're smoothing the data by aggregating, and you're washing away all the variability. So that's a problem. Another approach is the two-stage approach. And this is something I've kind of advocated to many people, which is you fit a curve to each person. Now, if they've got zero values, you've got to handle that using the different models of your choice. You get their individual alpha parameters and intensity parameters, and you statistically analyze those in some group comparison. And then you might fit a curve to the mean to just descriptively show those data. But there's limitations to this as well. And so, there's a really great piece in the Kaplan et al. Paper about this. So I'm just going to kind of put up some quotes for the sake of time. So fitting the means, it's not appropriate for statistical inference and is pretty much suitable only for descriptive graphical theoretical equation testing. But when you're potentially informing policy and you really want an accurate representation of something like Pmax or expected revenue from Omax, we want to make sure that that variability is being captured. Another approach that you can do, and Prism can do this, is you fit a curve to the pool of data. So it basically still goes through the means the way it would, but it's also letting the variability across all the participants impact the variance accounted for by the equation. And so this is a little bit better, but it implicitly assumes that all the data points are independent, which they're not. But there are some assumptions of nonlinear regression that we have to keep in mind when we do these analyses. So this can lead to incorrect standard errors for estimators. So there's an issue there. And then also the two-stage approach. This is something that we've talked about a lot in my lab because you often see this in your own data, I'm sure, where you have step response patterns. So someone on an alcohol purchase task for the first 3 prices might put 10, 10, 10. For the next 3 prices, it's 5, 5, 5, and then it's 0, 0, 0 all the way across. those data aren't great for fitting a curve. And so if those data aren't captured, or if it's 10, 10, 10, 10, 0, and now the model you're using doesn't allow you to do that, you might not even get an alpha value for that participant. So that then biases downstream analyses where you're doing comparisons between groups and you're favoring only the clean, quote unquote, clean data, where people's response patterns that are in that stepwise fashion that you might not be able to fit a curve to, those are valid, accurate data and representations of their preferences and demand. So we don't want to throw away real data. So there's that issue. And then also individual parameters are analyzed downstream with an implicit assumption of perfect accuracy. So again, we're kind of just assuming that the demand model for those individuals accounts for all the variance in their data when we get their intensity value or Pmax or Omax or alpha. We're assuming that's pure. That is exactly what it is, because we're not factoring in that they might have had very little variance accounted for by the model. And so it was a very messy data set. But we do have an alpha, and now we're going to plug it in to a regression or an ANOVA and assume that it's perfect. And so that's probably unwise. And then finally, it does not account for intra-subject correlations across experimental conditions. So Brent makes a very strong case for a mixed effect model. And so in his own words, it's an ideal method of incorporating the benefits of each approach in a single stage, using all available data, incorporating covariates and experimental factors. We often look at these at the second stage, but this then results in population level estimates. But it also gives you all those individual estimates. So this is like a win-win. So you have your cake and eat it too, so to speak. And so what this is doing, again, in his own words, simultaneously modeling underlying trends and effects, individual specific departures from these trends, so those random effects, and then it quantifies the error variance in the context of a single model. So just kind of to show you like what that might look like. Here's this, but for the sake of time, I'll point you to that paper to kind of make sense of all this. But you have all of these different curves from all these different participants. Now you're fitting one that's incorporating all of the error from all of that, as well as random effects. So even when you've got some of these outlier participants in blue, we still get usable data for our analyses. So there's a lot to consider here. I've thrown a lot at you. Some analyses are clearly more complex than others. So what I would say is be sure you have an a priori research plan and you select an analysis that's the most appropriate. I have a few more slides after this, just some good take-home points. I'm not completely wrapping up yet. But what I would say is don't be afraid to simply fit a curve to aggregate data to simply describe overall demand and keep your analyses to observed indices. And that's kind of what I've moved to as we kind of sort this all out in the model comparison world. I'm going to use my observed values, so self-reported intensity, self-reported Pmax, Omax values, breakpoints, and compare those in kind of that two-stage sort of approach, and have that other demand curve for simply graphical purposes only. That's just my opinion to simplify things a little bit, but if you need a model to take care of everything else, the mixed effects modeling is probably the best approach. Okay, so some of these issues that we've talked about with error variance and how you're handling things, and then what do you do with all the different K values, et cetera. Something that I've moved to in my own work, especially when doing policy level questions, is to consider modeling percent market consumption. And this was something out of Greenwald and Hirsch, which was referenced earlier today by Michael in his talk on purchase task, which is basically a binary sort of approach to a purchase task. So you ask people, would you purchase this commodity at this price? Yes or no? And this is really good for bulkier commodities or examining the valuation of something with low quantity consumption. So all those things that we do probability of purchase for, this might be a better way to do it. Like, what does it mean to say I have 75% likelihood of consumption? I don't know what that means. But what we can do is model what people say in terms of yeses and nos by looking at the proportion of the population that's saying yes at each price. And that's usually what a decision maker, a policy maker cares about. So that's one way to handle it. So we've used this for certain commodities I'll show you in a moment. But I will say, especially in the addiction world, this is straying a little bit then from things like quantity frequency of consumption. because we're not getting a quantity within subject at each price. So that's a consideration. So when we're doing this, what we're doing is saying that Q, rather than percent or number of reinforcers consumed, is the proportion of the sample consuming the reinforcer at each price. Or you could keep it simple and just say it's the number of participants out of the total who are consuming the reinforcer at each price. So we've used this recently for certain things with high face validity, like, for instance, accepting the COVID vaccine. So we modeled that, looking at different hypothetical vaccine efficacy as the unit price. And so this is a yes or no sort of thing. Like, I'm not going to get 10 doses of Pfizer, although we might have to end up doing that over time. But the assumption is this is a one-time decision, yes or no. And so we wanted to see if we frame this as standard FDA approval versus warp speed, what that would do to the critical mass of people to get this for herd immunity purposes, for example. So again, vaccine acceptance is a yes or no. This is a solution to doing that. Another paper that is online now is a condom demand paper. And this is by one of my doctoral students, Josh Harson. And what we did here was look at a situation where someone needs to purchase a condom for a sexual act. And we kept it to actual sort of retail market. So you had to buy an entire box of condoms for this one sexual act, but it's essentially purchasing a condom. We wanted to model for that single instance as like a state-based sort of demand thing, where you're really only doing one consumption value. You're purchasing one thing. And so what we did here was look at the proportion of individuals making that purchase at each price. And so this was a way to get around some of those issues. So there literally is no variability in consumption per se, but there could be some interesting things to model down the road in terms of logistic regression of yeses and nos as a function of price and so forth. But for now, this is kind of a simple way to do it. All right, so it's just some quick resources to throw at you as we wrap up. The demand curve analyzer that Sean Gilroy produced, and it's covered in this JEA paper, is really great. Here's a quick screenshot of what it looks like. You can download the software, get it from his website, which I'll share with you in a moment. But you essentially get your data. It might be in a Qualtrics output or something, or Excel. And so you have your price data, your consumption data, and you just copy and paste that into the solver. So column A is our prices, column B is consumption. And so what you do is just simply hit demand curve analysis, and you can specify what the columns represent. And so you don't need any software for this except to just download this open source software from his website. You then set the prices. And so again, the way you do this, you can actually input your data any way, as long as you're highlighting the data correctly. It doesn't need to be in long form or short form or any certain way. And then you can pick which model you want to use. So the linear, exponential, or exponentiated, these are the ones that are available right now. And as you make those choices, you can then make decisions about what you do with zero values. So there's prompts along the way to make sure that you're thinking through your approaches, because there are decision rules. You can output figures, you can do standardized demand figures, so everything's out of one. You can get Jeff Stein's systematic criteria out of this by clicking show always. What do you do when X is 0? Like when price is 0, do you fit something to that? Do you change it to a value? And if you're really good and want to get into different optimizing strategies, you can do that too. That's beyond me though. And then there's different approaches to K. And so there's a lot of stuff you can do here. And as you can see, the first thing that will happen if you check that box is you get data on how systematic your demand data are. And then do you want to use that in subsequent analyses? And then you get your plot for this participant. And so this is very easy to use. There's a tutorial in JEA, like I said. It will give you all of the values that you need for most purposes. So for instance, tells you what equation you used. It will get your alpha values, your error variances, all of that. Breakpoint 0, breakpoint 1 if you want it, essential value if you want it. It's all there. So this is a really nice open source package for people to get started in doing these analyses. Okay. Oh, and it also does Omax, Pmax, empirically derived versus just observed and so forth. So it's very, very robust. All right. Next, I would go to Brent Kaplan's GitHub page. You can download some great things there. So there are some data that go with the mixed effects demand paper I recommended earlier. The Bees demand package is available from there as well. If you're a user of R or someone who's at least versed enough in R to be able to run this package. Again, it's very robust and it does everything that you typically need to do for publication purposes. Jeff Stein, who I believe is still on this call, he has on his ResearchGate page to accompany his paper on non-systematic purchase task data, there is an Excel sheet that allows you to copy and paste data into, and that will allow you to get measures of how systematic those data are. Again, you should read the paper that goes with that. So Sean's website, smallendstats.com, also has a PMAX solver that is open source and available to you, as well as some delay discounting tools for those of you who are also in that line of work. My lab website also has a host of things. I have GraphPad Prism templates for cross-price elasticity, the different models of demand. I've also got some things on there for you to do the visualization of demand, etc. So be sure to check that out. And then in terms of the ZBE stuff, the IBR website, this is where Steve Hirsch maintains this. So there's GraphPad templates for exponential model, as well as a zero bounded exponential model, as well as a PMAX solver for both. So those are open for you as well. Those are freely available. All right, now these 4 papers, again, I am lucky enough to be a co-author on 3 of them, and I'm not recommending them because of that. But I do find that these are kind of the most comprehensive reviews of what's going on in the demand analysis and all the nuance that happens in those analyses. These slides are available on our hub, and so you could check that out there and look these up. You might have to email the authors for some of them because they're so new, but I strongly suggest before you fit your next demand curve, you read these papers to have a true, thorough understanding of what you're doing. My final case I'm going to make here based on some of the presentations I've seen earlier. These aren't in the slides that are available. I actually updated this. So always in your methods and results section, describe the following: the model that you used and why. That's important. So exponential, exponentiated, did you do the ZBE? Those are important things. People need to replicate what you did. Likewise, some people don't always specify whether they constrained a parameter like K or intensity. And so how and why you constrain those parameters would be important. And because I think K is so important, I actually have that as its own bullet. How did you calculate K if you're using K? In our systematic reviews that we've done, even including our own work, we don't always say how we got K. And so that makes it, again, very difficult for new users and new demand modelers to understand what to do, especially if they're trying to replicate your work. And then based on the new work on the mixed effects modeling, it's important to talk about how you modeled your aggregate data. Did you do the fit to mean approach? Are you looking at the pooled data? That's important to discuss. And of course, obviously, we should be discussing whether or not your metrics were derived by an equation or simply observed or obtained from the purchase task self-report itself. So for instance, Q naught, like what is that value? Did they put 10 or did the curve say it should be 10 based on the regression? So we need to make sure that we're specifying that. And then finally, and related to all of this, PMAX and OMAX are things that often get used, not always, but people often report it without specifying how it was calculated. And these can be observed versus derived. And in the derived approaches, there are often, there are several different ways you could even do that, different approaches to modeling that. So you just need to be honest and clear about what you did so people can better evaluate it. All right, so in closing, I want to say thank you to the following people who I've talked extensively to about demand modeling over the years. They appear in no particular order except to make a nice kind of like design on the slide. So if your name is lower on here, it's not any slight to you, it's simply to make it look pretty. So thank you to the following individuals for shaping this talk over the years. And thank you to all of you for listening to me kind of blow through this as fast as I could. Please keep in touch via email or on Twitter to talk more about this if you are so inclined. And I don't know if we have time for any questions, but I will stop here.